All right, so this mini lecture is going to look at the energy of a wave in motion through a medium. And if we think about a wave traveling through a medium, it's not too much of a stretch to be like, yeah, this is a transfer of energy through that medium. And so waves transfer energy. You can think of them as a transfer of energy through a medium. So what does that energy look like? All right, and what does it do? Well, it turns out that how that wave interacts with the particles of that medium is through simple harmonic motion. It causes these particles to vibrate in simple harmonic motion. So I encourage you to go back and, if that's a new concept for you to be thinking about, go back and check out the videos on simple harmonic motion so you can get a good framework of that concept. And you understand that we know the energy of simple harmonic motion of an elastic material in particularly is given by the relationship 1/2 times that material's spring constant K, it's related to the elasticity of that material, the spring constant K, times the amplitude of that motion squared. So that's the energy of a particle in simple harmonic motion. Now we also know simple harmonic motion has a periodicity, which means it has a frequency. That frequency is related to the wave in this case. So frequency is also related in simple harmonic motion. So the frequency of simple harmonic motion of an object in an elastic situation is given by 1/2 pi times the square root of the spring constant over the mass of that particular particle. So I have two relationships describing the behaviors of simple harmonic motion. And again, go back and look at that video. That's related to the wave, which is kind of cool. So I can take the energy and I can relate it to the frequency of the wave itself. So I'm going to solve for the spring constant in my frequency equation. I'm going to use that in my energy equation. So if I solve for K here, I find that K is equal to 2 pi times the frequency, that whole grouping squared, times the mass. And I'm going to use that then into my energy equation. So I can rewrite my energy in terms of the frequency. And when I do that, I find that my energy is equal to 2 pi squared times the frequency squared times the mass times the amplitude of that wave squared. All right, so you can do that. You can do that math on your own, but our energy, what does this tell us? It tells us that our energy is proportional to the frequency squared of our wave, and our energy is proportional to the amplitude squared. Maybe that's not too big of a stretch. I mean, the larger the amplitude, we might expect it to have more energy. The faster in terms of frequency, more frequent that the object is, that the medium is oscillating, the higher the energy. So those aren't necessarily a stretch conceptually, but we can see how they're directly now related to the frequency squared and the amplitude squared. Now, we often actually don't talk about energy very often directly when we kind of talk about things, but we do talk about the idea of power. So I want you to think back on when we learned about power in that forces, those force ideas, right, and energy ideas. So go check those videos out, the videos on power. But you'll be reminded that power was our energy over a certain amount of time, energy through time. Work, you'll see that it says work, and remember, work and energy are pretty tight. So that tells us if power is energy per time, this actually then tells us that our power is proportional to the frequency, and our power then is also proportional to the amplitude squared. So our power is proportional to the frequency squared, and our power is proportional to the amplitude squared. Again, probably not too much of a stretch. I mean, the idea is that the more energy I have, the more power I have, right? But let's take it one step further, because when we think about waves, we often think about intensity. So think about sound, and think about the sound intensity, and think about earthquakes, right? The intensity of the earthquake. So intensity intensity has a slightly different definition that I want to make sure we understand. Intensity is defined as the power, I'm using those 3 lines for a definition, the power transported across a unit area. Okay, power transported across a unit area that's perpendicular to the direction of energy flow. All right. So what does this mean? Well, we think if we imagine energy flowing outward in a sphere, consecutive spheres, right? Outward in a sphere. That the energy is going, if we imagine that sphere, the energy is going perpendicular to kind of the shells of that sphere as we go further and further out. So if we look at the unit area of that sphere, the intensity is, what is the intensity at any one of those shells as the energy is flowing perpendicular outward radially, maybe from the center of that sphere. So that kind of gives you a framework of the intensity. We're actually going to look at that 3-dimensional model of intensity. So if I take this definition and I pull it into an equation, this tells us that the intensity is equal to the power through that unit area. And again, if we imagine that that wave is traveling in all dimensions, okay, so from a source outward, that's a sphere. And the unit area of the sphere is 4 pi r squared. So this, remember, is the area, surface area of the sphere. Okay. All right, so what does that tell us? Well, we know that the intensity then is proportional to 1 over the radius squared, right? So I just looked at this relationship and we can see that the intensity is proportional to the radius squared. Probably not too drastic of a statement, right? Because we might imagine if somebody has a source of sound and that sound is emanating out in a sphere-like way, the further away I am, the less intense that sound is, right? The less intense that sound is. This is what's known as the inverse square law, and we see this in other things in physics, so it might look familiar to you, or you'll certainly see it again. All right, so what does that tell us? I am going to run out of a little bit of room here, so I'm going to erase now the energy information. Let's just look at this idea conceptually. And again, it hopefully will get you to oh yeah, that makes sense from my experience, right? It tells us that the further away we are from the source of that wave, the less intense it is. All right, well, that makes some sense. Okay. And, erase. We can look at that also in terms of power and also in terms of the amplitude. Okay, so if I want to look at what's the intensity at one location relative to the intensity at another location, we get a relationship for intensity and position that's going to be very useful for us as we look at how waves energy and how wave intensity changes. So we know that the ratio of the intensity at a second location and the intensity at a first location, not ration, but ratio, we can write that in a relationship. The intensity at position 2 is equal, of course, to the power at position, the power is the source of the wave, over 4 pi times r2 squared. And the intensity at position 1 is the power over 4 pi r1 squared. Now remember, power was not related to the distance. Power was related to the energy, right? The energy per time. Okay, so power, if I take the ratio of these two, so I2 to I1, I end up, p's cancel, the 4 pi's cancel, I end up with the ratio of the distances squared. So this becomes a useful ratio for us to be working with in terms of intensity of the wave. Okay, useful ratio. What does it tell us? Well, let's just do a quick example. If I double the distance, what happens to my intensity? So if I double the distance, what happens to my intensity? I'm going to use this relationship. Well, the intensity at the new distance, I2, is going to be equal to R1 squared over R2 squared times I1. If I double the distance, I have 2 R1 in the bottom. So I have R1 squared over 2R1 squared times I1. And I find out that I get 1/4 the intensity when I double the distance. So that's, again, an example of the inverse square law, how we can use this relationship to get a sense of how intensity changes the further I go from the source. Okay. We also know that intensity is related to the amplitude of the wave. And we know that because power is related to the amplitude of the wave. Intensity is related to power, and power is related to amplitude because energy is related to amplitude. These are all related, right? So if we know that the intensity now is proportional to the amplitude squared, again, because power is proportional to the amplitude squared. That means, and keep in mind, intensity is proportional to 1 over the distance squared. And that tells us that the amplitude squared is proportional to 1 over the distance squared, which tells us that the amplitude is proportional to the distance, 1 over the distance. So, does that make sense? As I get further and further away from the source, does my amplitude go down? Yeah. So, in this way, intensity is related to amplitude, which you might kind of intuit. But if we also think about a water wave, the further away you are from the boat, the wave gets less and less high, right? So if you're really close to the boat on your little floaty in the water, whew, you go really high. But if you're more closer to the shore, you go a little bit up and down. So this also gives rise, similar to what it did with our intensity, it gives rise to a useful equation for us to look at relative amplitudes of waves at different distances from the source. So in the same way we did for intensity, we come up with the relationship that the ratio of the amplitudes is the inverse ratio of the distances. So let's just do a quick example of that because it's slightly different than the intensities. It's going to give us a different number, so just to clarify those things. So imagine that I am twice the distance. Again, twice the distance, so that the distance of R2 is 2 times the distance of R1. How does the amplitude of that wave change? Right? Well, taking this equation, we have the amplitude is equal to, of this new position, is equal to the ratios of the positions times the amplitude of that position. And we get R1 over 2R1. And so the new amplitude is half. So as we move, when I double the distance, I have the amplitude. All right, so This relationship is going to be pretty useful for us. I will rewrite the intensity relationship. For you, that is going to be pretty useful for us. And then recognizing that intensity is related to the square of the amplitude through that power and energy. All right, good job.